We can see edges to our cosmic map, but those edges aren't the end of reality. We talk about the observable universe like it's everything. That's a mistake. A deep one. What's beyond our horizon is a profound mystery. It reshapes how we understand existence. The cosmos isn't just an island of stars. It could be an infinite ocean. And we've only seen a drop. We'll look at how the universe might be shaped, how it got so immense, what that means for the fate of everything, the possibility of other worlds, other realities, even other versions of ourselves. This expands your perception. A universe without end. What does that mean? The cosmic horizon is a kind of prison. But it's a prison made of light. Picture yourself as that astronaut, floating in a dark ocean. You turn on a flashlight, and a sphere of light just blooms around you. It shows you what it can touch. Everything outside that sphere is just gone, swallowed by the void. That beam of light is your only link to the universe. Now take that flashlight, replace it with the most powerful telescope we could ever build, and point it everywhere. The sphere of light, you can see every photon that's ever reached your eyes or your instruments. That's the observable universe. It's our collective flashlight beam. This sphere is huge, roughly 93 billion light-years across. But the crucial point is this: it's not a wall. Not rock or energy, not something you could crash into. It's a horizon, a limit set by two simple rules. The universe has an age, about 13.8 billion years. And light has a speed, a universal speed limit. Nothing goes faster. So the most distant light we can possibly see is the light that left its source 13.8 billion years ago. And it's been racing toward us ever since. That light defines the edge of our visible reality. Beyond that edge, there are galaxies, stars, maybe entire civilizations. But their light hasn't had enough time to reach us yet. They're cut off from our reality, causally disconnected. Their events can't influence us. Ours can't influence them. This horizon isn't a permanent cell, though. It's slowly expanding, every year, every second. Light from regions just beyond the old horizon finally completes its journey and enters our view. The prison walls are rolling back gradually, imperceptibly, but they roll back at the speed of light, and the universe beyond them is likely expanding even faster. So we're forever chasing a horizon we can never catch. That's the fundamental condition. We're not at the center of this sphere. The universe has no center. Every observer on every planet in every galaxy has their own observable universe, their own unique sphere of light. Ours is special only to us. Grasping that is the first step. It's humbling. Our entire scientific story, everything we know about cosmology, is written inside this glowing sphere. But to assume the story ends at its edges is a mistake. It's mistaking the page for the whole book. The true nature of the cosmos, its shape, its ultimate size, that's written in the darkness beyond. That expanding light isn't just out there in empty space. It's part of the fabric of spacetime, and the shape of that fabric, that's the universe's biggest secret. Is it finite like a bubble, or is it infinite, stretching forever? The answer is geometry, not shapes on a page, but the geometry of reality. Think of a balloon, a party balloon. You blow it up, every dot on the surface moves away from every other dot. There's no center on that rubber skin, no edge. An ant living on that balloon would think its whole universe was expanding, with no beginning or end to the landscape. That's a two-dimensional picture for our three-dimensional expansion. Every galaxy is like a dot on that balloon, carried apart as space itself stretches. So what's the overall shape? Cosmologists have three possibilities. The universe could be positively curved like a sphere. In a spherical universe, if you traveled in a straight line, you'd eventually loop back to where you started. Finite but with no boundaries, a closed loop, or it could be negatively curved like a saddle or a Pringle chip. In that saddle-shaped universe, parallel lines would diverge. Space would feel warped, expansive. The third possibility is that it's flat, perfectly, geometrically flat. In a flat universe, the rules from school hold true. Parallel lines stay parallel. Triangles add up to 180 degrees, and this isn't just theory. We've measured it. Satellites like the Planck mission studied the afterglow of the Big Bang, the cosmic microwave background. They looked for any warping, any hint of curvature. The data is clear. To the limits of our measurement, the universe is flat. That finding is monumental. A flat geometry means a universe that could be infinite. If the universe is flat and infinite, then our entire observable cosmos, that 93 billion light-year sphere of everything we can see, is just a speck. An infinitesimal bubble in an endless ocean. Our horizon isn't the shore. It's just how far we can see from our little raft. This geometric insight changes everything. It turns the observable universe from everything that exists into everything we can currently see. Our local neighborhood in a metropolis with no end. And once you accept we might be in an infinite flat universe, the implications become staggering, even unsettling, because infinity isn't just a big number. It's a concept that rewrites the rules. A flat geometry means the universe is infinite, but how did it end up that way? You have to go back to the very beginning. To a fraction of a second so small it's almost impossible to think about. That's the era of cosmic inflation. The theory says the universe didn't just start expanding. It exploded into being. For a tiny instant, a patch of reality smaller than a single proton went through this violent, exponential growth. It stretched faster than light. And this wasn't matter moving. This was space itself being created, unfolding at a rate that makes every explosion we know look completely still. In that blink, a region you could hold in your hand, if you could hold a quantum foam, was stretched to a size larger than everything we can see today. All of it, every galaxy, every star, every planet, all came from a seed smaller than an atom. Inflation was the engine of immensity. It didn't just make things big. It ironed everything out. It explains the uniformity we see in the cosmic microwave background. That ancient afterglow is almost perfectly smooth. The temperature is the same in every direction. To 1 part in 100,000. That only makes sense if the entire observable universe was once a tiny, connected region. A region that got stretched so fast it never had time to develop major wrinkles. And it explains the flatness. Imagine a tiny, crumpled piece of paper, a wrinkled ball, and then you stretch it over the surface of the Earth. The local curves and bumps vanish. The paper appears flat. Inflation did that to spacetime. It stretched the initial quantum wrinkles so much that on our scale, the universe looks perfectly geometrically flat. But this is where it gets mind-bending. Inflation might not have been a one-time event. It might not have stopped everywhere. The leading idea is called eternal inflation. Think of a pot of boiling water. Our universe is one bubble that formed in that seething, inflating broth. Our bubble stopped inflating, it cooled. It gave us stars and galaxies. But the broth outside our bubble, it's still boiling, still inflating at that insane, exponential rate. And in that inflating meta-universe, new bubbles are constantly forming. Each one a separate pocket universe with its own laws of physics, its own version of reality. Our entire cosmic horizon, that 93 billion light-year sphere of everything we can see, is just our local bubble, one island in an infinite, eternally inflating ocean. This pushes the idea of scale from the merely large to the incomprehensibly vast. We're not just looking at a universe bigger than we can see. We are likely living in a multiverse, a reality where our story is just one paragraph in a library that has no walls and no end. The uniformity is a puzzle. It kept people up for night after night. You look at the cosmic microwave background, that ancient light. In one direction, the temperature is 2.725 Kelvin. You look in the exact opposite direction, 13.8 billion light-years away. The temperature there is also 2.725 Kelvin. They match 1 part in 100,000. That's the horizon problem. In the classic Big Bang model, those two regions of the sky could never have exchanged information. They were too far apart. Think of two people in a dark field, miles apart. One lights a match, the other won't see it. Their environments are separate. For them to have the exact same temperature, they would have had to coordinate to reach equilibrium. But in the old model, there wasn't enough time. Not enough time for light to travel between them. They were outside each other's causal horizons. So how did they arrange this agreement? It's like walking into two sealed rooms on opposite sides of the planet, and finding the thermostat in each set to exactly 72.5 degrees. You'd suspect they were once part of the same building, connected by a central system before the walls went up. And that's what cosmic inflation tells us. The solution is simple. Those two distant regions of the cosmos, which appear to have never met, were once connected. They were neighbors. In the first sliver of a second, the entire observable universe was compressed into a space smaller than an atom, a space where every point was in contact. It was a unified seed. Then inflation happened. That seed underwent hyper-fast expansion, stretching space faster than light could cross it. It took those once connected regions and blew them apart. To opposite ends of our visible sky, the perfect temperature match isn't a coincidence. It's a memory, a fossilized imprint of their shared origin. The cosmic microwave background's smoothness is the oldest family portrait, a snapshot from when everything we see was close enough to touch. This is our clue. The uniformity we observe isn't just a feature of our local bubble. It's a signature that our entire observable universe came from a tiny, connected piece of a much larger reality. That original seed from which our 93 billion light-year sphere grew was likely just a fragment of an even grander structure. The walls of our observable horizon are not the walls of creation. They are just the boundaries of what we can currently see. From a single point within an immeasurably vast cosmos, the horizon problem, once a deep mystery, becomes the evidence that our home is part of something far grander. The silence of the night sky, that sameness in every direction, is not emptiness. It is the echo of a shared beginning, whispering that we are all connected to realms forever beyond our sight. Our local bubble is perfectly flat, and that flatness points to something deeper. It brings us to the multiverse, which sounds like science fiction, but it's a real theoretical framework. Not one single idea, more like a whole hierarchy of possibilities, realities beyond what we can see. The simplest version comes straight from an infinite, flat universe. If space really is endless and matter can only arrange itself in so many ways, then everything that can happen will happen, an infinite number of times. Somewhere out there, in a galaxy just like ours, on a planet just like Earth, there's a version of you reading a version of this. Somewhere else, a version where you chose something different this morning. Infinity makes that certain. That's the level 1 multiverse. It's not a separate place with different laws. It's just more of the same universe, so vast that every possible arrangement of particles repeats. Our observable sphere is just one neighborhood in an infinite city, and in that city, every street has a twin, every house, but inflation suggests something stranger. That eternally boiling broth of spacetime. Our universe is one bubble where the boiling stopped, where inflation ended and stars could form, but other bubbles formed with different rules. In that seething meta-universe, new pockets keep nucleating. Each one could have different constants, a slight tweak to gravity's strength, or the mass of an electron. In most of those bubbles, the physics wouldn't allow atoms, let alone planets or life. We don't live in a special bubble. We just live in one of the rare ones where the numbers lined up. That's the Level 2 multiverse, a cosmic foam of disconnected realms, each with its own rulebook. Then theories like string theory add more layers, a Level 3 multiverse from quantum mechanics, where every quantum choice, every possibility, branches into its own reality, and some models suggest entire universes could exist as parallel membranes. Brains floating in a higher dimensional space, sometimes colliding with unimaginable consequences. The point is, the word universe isn't big enough anymore. Cosmologists use multiverse for the totality of everything. Our whole cosmic story, the Big Bang, the galaxies, that's just the local history of our bubble. Our horizon shows us one room, but the building has countless floors, endless wings, an architecture we're only starting to guess at. That doesn't make our reality insignificant. It reframes it. We're not the center of everything. We're witnesses to one particular expression of reality, a single thread in a tapestry of infinite variety. The cosmic microwave background, that faint glow everywhere in the sky, it's the afterglow from when the universe was just 380,000 years old. Before stars, before galaxies, everything was a hot, dense fog. Then the cosmos expanded and cooled, and the fog cleared. Light that had been trapped could finally travel. That first flash is still traveling, and we can see it. The CMB is a snapshot of the infant universe, a baby picture of everything, our deepest observational probe. A direct line to the beginning, but even this window has its blinds. The radiation we detect comes from a specific, distant shell, a surface called the last scattering surface. That's the limit of what this light can show us. Imagine standing in the center of a giant hollow sphere. The inner surface of that sphere is glowing with a pattern. That pattern is the CMB. That sphere is fixed at a distance of about 13.8 billion light-years away in every direction. It marks the moment the cosmic fog lifted. It's the inner surface of our observable horizon, the oldest light that can possibly reach our eyes. We study the patterns on this shell with incredible precision. Tiny temperature fluctuations, variations of just 1 part in 100,000. They're not random. They are the seeds of all structure. The slightly denser patches, shown as slightly warmer spots, are the gravitational seeds. Over billions of years, they pulled in matter to form the cosmic web of galaxies and clusters we see today. By analyzing these patterns, we've learned the universe's geometry is flat. We've measured its composition: dark energy, dark matter, ordinary matter. The CMB is the Rosetta Stone of cosmology, but here is the limit. This shell is a boundary. Like an observer on a foggy island can only see the ocean to the horizon, we can only see back to this surface of last scattering. The CMB tells us the story of our local cosmic bubble, from its infancy to that moment of transparency. It cannot tell us what lies beyond that shell. It is a window, but the view stops at the horizon. We are looking at the inside of our own cosmic eggshell. We can study its texture in detail, but we cannot see what's outside the egg. Yet there is a possibility: shadows. If there are colossal structures beyond our horizon, regions of vastly different density, or even the gravitational influence of other cosmic bubbles in a multiverse, they might leave an imprint. A subtle distortion in the pattern of the CMB, like a distant mountain range casting a long shadow on a valley floor at dawn. Cosmologists scour the data for these anomalies. Large-scale asymmetries, strange correlations that shouldn't be there. Some have been found, mysterious alignments called the axis of evil, a large, unexplained cold spot. Are these statistical flukes in our limited map? Or are they the faint fingerprints of something vaster? Could they be bruises on our bubble from a collision with another universe? These questions remain open. The cosmic microwave background is our clearest window to the beginning, and it's our most poignant reminder of our limits. It gives us the story of our home, but the very perfection of its data hints that our home is part of a story too large to read from a single page. It whispers that the map we hold is complete, but the territory it represents is just the first chapter. That ancient light gives us the blueprint, but the structure it built is all around us. You look beyond the individual stars, the galaxies, and you see the universe's true architecture. It's a web, a vast three-dimensional tapestry, light and dark matter woven together by gravity over billions of years. Galaxies aren't scattered randomly. They gather into clusters, and those clusters connect along these immense, thread-like filaments that stretch for hundreds of millions of light years. And between them are the cosmic voids, enormous, nearly empty regions of space. They can span hundreds of millions of light years across. That's the cosmic web. The large-scale structure of everything we can see, and within this web we've found titanic features, the Sloan Great Wall, one of the largest known structures. It's a colossal filament of superclusters, roughly 1.4 billion light-years long. Light leaving one end when the first complex life was forming on Earth would only be arriving at the other end today. It's not a solid wall, it's a gravitational spine, a river of galaxies flowing through the darkness. Then there's the Hercules Corona Borealis Great Wall. A proposed structure so immense, some 10 billion light-years across, that its very existence seems to challenge our understanding. A structure that large would span a significant fraction of our entire observable horizon. It makes you wonder, is that a statistical fluke within our bubble, or is it a clue, a hint of organization on a scale we're only beginning to perceive? These great walls and voids, they're not built from stars alone. They're shaped by the invisible scaffolding of dark matter. After the Big Bang, dark matter which feels gravity but not light began to clump first. It formed a gravitational skeleton across the cosmos. Ordinary matter, the gas that would become stars and galaxies, was then drawn into these dark matter wells. The cosmic web is in essence a map of dark matter's hidden geography. The light we see merely traces its contours. Now take this concept, the cosmic web. The gravitational collapse, the endless dance of structure formation, and place it inside an infinite, flat universe. If the universe is truly homogeneous on the largest scales, if the cosmological principle holds, then this pattern doesn't stop at our light horizon. It continues forever. The Sloan Great Wall in our neighborhood isn't unique. In the cosmos beyond our view, there are other great walls, other immense filaments, other vast voids, an endless repetition of this cosmic architecture stretching into infinity. Our entire observable universe, with all its 100 billion galaxies, becomes a single panel in an infinite tapestry. The largest structures we can measure become local features, merely the pattern of the wallpaper in our room, in a mansion with an infinite number of rooms. That shifts the goalposts of our imagination entirely. We're accustomed to thinking of the universe as a container with things inside it. But if it's infinite, it's not a container. It's the fabric of existence itself, and the great walls we see are not objects in space. They're wrinkles in that fabric, patterns in an endless weave. Contemplating this is less about adding more zeros to a distance. It's more about redefining what everything means. The scale becomes not just spatial, but existential. We're not just looking out at a big universe. We're embedded within a reality whose structure, whose very texture, repeats without end. And somewhere, in the darkness beyond our horizon, another observer is looking out at their own great wall, wondering if they are alone in the cosmos. The web we see is huge, but it's also temporary. That cosmic horizon isn't a fixed line, it's a moving target. And what controls that motion is the universe's biggest mystery, dark energy. It's not a substance you can touch. It's a property of space itself, a kind of pressure in the vacuum that makes the expansion of the cosmos accelerate. Two teams of astronomers found this in the late 90s. They were looking at distant supernova. They expected to measure how fast the universe's expansion was slowing down from gravity. But they found the opposite. The most distant explosions were fainter than they should have been. They were farther away. The expansion wasn't slowing. It was speeding up. Something was pushing galaxies apart. We call that something dark energy, and that changes everything about the cosmic future. Think of our observable universe as a sphere of light. It grows as new photons cross into it. That sphere is still getting larger. New galaxies keep entering our view, but because space itself is stretching faster and faster, the most distant galaxies are being carried away at speeds that will eventually exceed light speed. Not because they're moving through space, but because the space between us is being created so fast. When that happens, the light they send out will be fighting a current it can never beat. It'll be stretched into oblivion. Its wavelength pulled so far it becomes undetectable. That galaxy will have crossed our cosmic event horizon. It'll fade from view. Not in a flash, but in a slow, inexorable reddening into darkness. The result is a future horizon, a shrinking island of accessibility. Right now, we can see galaxies over 13 billion light-years away. In the far future, civilizations looking up will see only their own local cluster of galaxies, held together by gravity. The rest of the cosmos will have vanished behind a veil of expansion. All evidence of the Big Bang, the cosmic microwave background, will have redshifted beyond detection. The universe will appear static, island-like, and profoundly lonely. For those future observers, the idea of a vast, expanding cosmos will be a historical footnote, deduced from ancient data. The true scale of the universe will be permanently hidden from them. So the vast majority of galaxies that exist right now are already on a one-way trip out of our future. We see them today, but their light is a message from a past when the universe was more connected. They're ghosts in our sky, destined to disappear. The accelerating expansion is actively taking the cosmos away from us. It's creating a prison not of space, but of time. We live in a privileged cosmic era, a narrow window where we can still see the evidence of the beginning and infer the immensity of what lies beyond. This window is closing, so when we talk about the true scale of the universe, we have to include not just the space we can't see now, but the space we will never, ever be able to see. It's a scale defined by loss, a horizon that recedes faster than our curiosity can chase it. The accelerating expansion means the ultimate nature of reality, whether it's infinite or a multiverse or something stranger, might stay forever beyond our empirical grasp. We're left to piece together the puzzle from the fragments that haven't yet slipped away. That accelerating expansion points toward a lonely cosmic future. But maybe the loneliness isn't real. What if the vastness we see, the whole three-dimensional theater of stars and galaxies, is actually a kind of projection? That idea leads to one of the most radical concepts in physics, the holographic principle. It starts with black holes. Back in the 1970s, a physicist named Jacob Bekenstein proposed something startling. He said a black hole's entropy, which is a measure of its hidden information, is proportional not to its volume, but to the area of its event horizon, the surface area. Later, Stephen Hawking showed that black holes do emit radiation. They have a temperature that linked thermodynamics, gravity, and quantum mechanics in a deep way. And the key insight was this: all the information about everything that ever fell into a black hole isn't lost inside. It's encoded, pixelated, on the two-dimensional surface of its horizon. The three-dimensional interior is a projection from that two-dimensional surface, like a hologram. Now take that idea and apply it to the whole universe. The holographic principle suggests our universe might work the same way. All the information that makes up our three-dimensional reality, every star, every planet, every thought you've ever had, could be encoded on a distant, two-dimensional surface that surrounds us. That surface is our cosmic horizon, the boundary of everything we can observe. In this view, the galaxies we see, the space we move through, it's all an illusion. A cosmic projection. We aren't living inside a volume, we're living on a screen, and the true scale of the universe isn't measured in light years, it's measured in bits. Information density. Think of a credit card hologram, that flat, shiny sticker. You tilt it, and a three-dimensional image seems to float in space. The depth is an illusion generated from flat data. The holographic principle says our universe is that illusion on the grandest scale. The data is written on the spherical shell of our cosmic horizon. And we are inside the projected image. That turns the idea of beyond the horizon upside down. If reality is holographic, then asking what's beyond our observable bubble might be the wrong question. The outside isn't more space like ours. The outside is the projector. The cosmic horizon isn't a barrier we can't see past. It's the source code. The complete description of our entire reality exists there on that surface. The three-dimensional world we experience is a kind of shadow, a lower-dimensional representation of that richer information. This principle blurs every line we hold onto. Inside and outside, here and there, real and projected. It suggests the ultimate nature of reality isn't spatial, but informational. The universe isn't a place, but a process. A computation, and the true scale of everything becomes a question of how much information can fit on a surface, how complex the code can be. It's a staggering leap. It means that searching for what lies beyond our horizon in the traditional sense might be like a character in a video game trying to break out of the screen by moving forward. They can't. Their entire world is generated by rules operating at the boundary of their perception. For us, that boundary is the cosmic horizon. The holographic principle doesn't dismiss the vastness. It redefines it. The immensity isn't out there in more space. It's in the unimaginable complexity of the information that paints our reality into being. We are, in the most literal sense physics allows, living inside a story, and the cover of the book is the edge of our sky. The holographic principle changes how we think about reality. But the same equations that first describe the cosmos point somewhere else too. They point toward an infinity of space. The idea of a universe without end comes from math that's over a century old. Albert Einstein's theory of general relativity. It gave us equations for how matter and energy bend spacetime, and those equations have different possible answers for the shape of everything. Some answers describe a universe that curves back on itself, finite but with no edge like the surface of a sphere. Go far enough and you'd come back to where you started. Other answers describe a universe that's just flat and infinite, a plane that goes on forever. The math doesn't choose for us, it gives us a list, and we have to use observations to see which one fits. The measurement is curvature. For decades, cosmologists have used the cosmic microwave background as a tool. They look for any sign that parallel lines bend on the largest scales. The latest data from missions like Planck is precise, very precise. The universe is flat to within a margin of error of just 0.4%. That measurement doesn't just hint at flatness, it requires it, and a flat geometry in general relativity means a universe of infinite size. It's the simplest solution that fits all the data. We can't see infinity, of course. Our horizon blocks the view. But the equations, backed by observation, tell us that what's beyond that horizon isn't a wall. It's more of the same, more cosmic web, more great voids, more island galaxies continuing. This leads to a mathematical certainty that feels philosophical. In an infinite universe, anything that's possible, anything with a non-zero chance of happening will happen, not just once, an infinite number of times. It's a direct result of statistics applied to an endless landscape. Somewhere right now, a planet just like Earth orbits a star just like our Sun. On that planet, a civilization with our history, our art, our conflicts is happening. Somewhere else, a version of you made a different choice years ago, leading to a completely different life. And in other places, realities so alien we couldn't understand them are playing out. Infinity makes all of these not just possible, but inevitable. It turns the universe into a tapestry where every pattern that can exist does exist and gets rewoven forever. This isn't just speculation. It's the logical end of the flat universe model our measurements support. We can never have proof of another Earth, but the math says in a truly infinite cosmos, the number of perfect copies is itself infinite. Our local domain, with its hundreds of billions of galaxies, becomes statistically insignificant. A single grain of sand on a beach that never ends. That perspective is humbling. It redefines our place, not as the center of a finite creation, but as one conscious point in an endless field of possibilities. The equations don't just describe the stars. They describe a reality of such scale that our entire story is both unique and endlessly repeated. A silent fact that in a cosmos without boundaries, every story is being told somewhere in the dark. Infinity is mathematically certain in our equations, but science has a horizon. There's a line between what we can know and what's just a possibility. Our theories, cosmic inflation, a flat universe, give us a framework. They suggest the observable universe is a tiny patch of something much larger. That's a scientific inference. Built on measurements, on mathematical consistency, we can look at the cosmic microwave background, the large-scale structure, and say the evidence strongly suggests there's more out there. Much more. That's extrapolation, following the data as far as it logically goes. But we have to be honest about where the data stops. Science is about testable hypotheses. We can build models, bubble universes, infinite repetitions, holographic boundaries. They're self-consistent, mathematically fascinating. They help us think. But anything specific about regions beyond our light cone, their structure, whether they contain copies of us, different physical laws that enters a different domain. Theoretical physics or philosophy, we can't gather a single photon from there. We can't run an experiment beyond the horizon. That's our fundamental condition. Our cosmic solitude, this boundary isn't a wall to curiosity. It's the frontier of cosmology, recognizing it is intellectual honesty. The scientific method thrives on this tension. It lets us build castles in the air while keeping our feet on the ground of evidence. We can wonder, we can model, we can dream about the ultimate nature of reality. But we have to distinguish between the map drawn from data and the territories we can only imagine. That doesn't diminish the wonder, it refines it. It means the greatest questions: is the cosmos infinite? Are we part of a multiverse may forever hover at the edge of knowledge? They become guiding stars, not destinations. Our journey is to push that horizon as far as we can. With every tool and telescope, while accepting that some mysteries might be woven into existence itself, just beyond our grasp, the universe may hold its deepest secrets in a darkness light can never cross. The displacement is the last step. It's the deepest one. Copernicus took us out of the center of the solar system. Hubble showed our galaxy was just one of billions. And now the scale beyond the horizon tells us we're not at the center of reality either. Our whole story might be a single paragraph in a library that has no last page. That's more than a scientific fact. It's a philosophical earthquake. Because if the cosmos is infinite and uniform, then statistical certainty takes over. Every possible arrangement of matter has to happen, not just once, an infinite number of times. So somewhere, right now, there's a planet identical to Earth. And on it, a civilization with our history, our art, every detail. There's a version of you hearing these same words, and another version who made a different choice this morning, living a completely different life. In an endless cosmos, every story that can be told is being told forever. That idea challenges what we think is unique. Our consciousness feels singular. A private narrative, but if infinite copies exist, what does that mean for identity? Is the essence of you tied to the specific atoms in your body, or is it the pattern they represent? If the pattern repeats, does the conscious experience repeat with it? These are questions without answers, but they force us to reconsider the preciousness of our individual moment. It reshapes how we see our place in cosmic history too. We often use anthropic reasoning. We ask why the universe seems so finely tuned for life. The answer in an infinite cosmos is stark. We don't live in a special universe. We live in one of the rare bubbles, one of the rare planets where the numbers accidentally allowed stars and chemistry and biology to form. We are here because we couldn't observe a universe where we weren't. Our existence isn't a purpose, it's a possibility, one that occurred within a vast landscape of silent, sterile emptiness. This realization isn't meant to diminish our experience. It's meant to frame it, to give it absolute cosmic context. The love you feel, the art you create, the struggles you endure, they are no less meaningful. Their meaning doesn't come from being the only instance in all of creation. It comes from being lived, from the fact that within this local bubble of reality, consciousness has ignited. And it asks these very questions. We are the universe observing itself, and that act of observation in this particular place and time carries its own weight. The scale beyond the horizon offers a choice. We can see it as rendering us insignificant, lost in an endless repetition, or we can see it as revealing a cosmos of unimaginable richness, where every possible form of beauty and tragedy and wonder is expressed. Our chapter may be one of countless copies, but it's the only one we will ever read. And in that reading, in this shared moment of curiosity under a finite sky, we touch the infinite, the galaxies, the great walls. They're just the visible part. The embroidery on something much darker, most of the mass in the cosmos, the stuff that actually holds it together, we can't see. Dark matter, it's the silent partner, makes up about 85% of all matter. We only know it's there because of gravity. It bends light around galaxies. It decides how fast stars orbit. It created the wells where ordinary matter fell in to make the first stars, the first galaxies. Without that invisible scaffolding, the universe would look completely different. In our observable region, we can map its influence. Dark matter forms this vast filamentary web, a cosmic skeleton. The galaxies we see are just ornaments hanging from it. The great voids between clusters aren't really empty. They're just thinner patches in the dark matter distribution. That web is the foundation of our local reality. Now take that idea and push it past our light horizon. If the universe is infinite and uniform, this dark matter web doesn't just end, it goes on forever. An endless, repeating lattice of gravitational potential, stretching into absolute darkness. In that scale, statistical variation becomes a certainty. The overall pattern might be similar, but there could be regions where the dark matter is far denser than anything we see, places where it's collapsed into forms we can't predict. Structures so large with gravity so strong, they might defy our local physics. Monolithic dark matter halos with no stars, silent mountains of gravity in the void. Or think about other universes in a multiverse. In other pockets, the properties of dark matter could be different. Its particles might interact with themselves or with forces we don't know. In those separate realms, dark matter might not form a diffuse web at all. It could clump into dark planets, dark stars, even dark galaxies evolving on a completely different timeline. A cosmos where dark matter isn't just the scaffolding, it's the entire building. A reality of shadow and gravity where no light is ever kindled. Our effort to identify dark matter here with underground detectors, particle colliders, it's an effort to understand the most common substance in existence. Every experiment that fails, every new constraint we place, teaches us what dark matter is not. The process is slow, it's difficult, but it's crucial. Because until we understand this dark foundation, our models of the greater cosmos are incomplete. We're trying to describe an infinite tapestry while only feeling the threads nearby. The true distribution of dark matter, its behavior on scales far beyond our horizon, is still one of cosmology's great unknowns. It's a reminder that even the most fundamental parts of reality might hold surprises on the largest stage. The darkness between the stars isn't empty. It's full of a mystery that shapes everything we see and everything we never will. The dark matter web holds galaxies, but it also shapes the empty spaces between them, the cosmic voids. These are the true deserts, enormous regions, some hundreds of millions of light years across, where there are almost no galaxies. They're not perfect vacuums. A few isolated galaxies might drift through, but compared to the filaments and clusters, they're profoundly empty. The Boötes void is one of the largest we know. It's a spherical region about 330 million light-years wide. If the Milky Way were at its center, we wouldn't have seen another galaxy until the 1960s. That's the scale. It's not a hole, it's a valley in the gravitational landscape, where the dark matter density is so low, nothing was pulled together to form galaxy clusters. These voids are part of the cosmic web's texture. They're the negative space that defines the positive. Now, think about that texture in an infinite universe. The voids we can see Boötes, the local void we border, they're just our local examples, a statistical sample. If the universe is uniform and infinite, then this pattern of filaments and voids doesn't end. It repeats forever, and in that endless repetition, probability takes over. Could there be voids so large they make ours look like tiny bubbles? Regions where, for not just hundreds of millions, but for billions of light years, the density of matter approaches true zero. An emptiness so vast that light crossing it would find no galaxy for an eternity of travel. It's mathematically plausible. In an infinite cosmos, every possible configuration must occur, including voids that dwarf our entire observable universe. This leads to a possibility. The texture of the greater cosmos might not be a simple web, it could be fractal. An endless hierarchy where every filament contains smaller voids, and every void contains smaller filaments, on scales unimaginably large and small. Our entire observable sphere, 93 billion light-years, could in principle be sitting inside one of the larger voids of a supercosmic web we can never see. We study the voids within our horizon to understand our neighborhood, to take a census of cosmic texture. By measuring their sizes, distributions, shapes, we get a statistical model. A model we can extrapolate with caution to the universe beyond our sight. That model paints a picture, a reality defined more by absence than by presence. A texture of profound, yawning emptiness, punctuated by rare, brilliant islands of light and structure. We live on one of those islands. Looking out, we see other islands across a dark ocean. But the true nature of that ocean is one of vast, silent depths, where the spaces between the lights are not just gaps, they're the dominant feature of existence. This is the likely fabric of the infinite. Not a dense sea of stars, but an endless, structured void, with our galaxy as just one small, flickering point of warmth in the eternal cold. Our cosmic neighborhood has a likely end. The expansion keeps accelerating, galaxies will fade, stars burn out. Over trillions of years, even protons might decay. What's left is a cold, dark, dilute sea of particles. A permanent, silent freeze. That's the heat death, the predicted fate for our observable bubble. But that's a local forecast. It only applies to the neighborhood defined by our light cone. In an infinite cosmos, the idea of one universal fate just dissolves. Think of an endless forest. In one clearing, a great tree has fallen, rotted, returned to the soil. That clearing is in decay. But just over the next ridge, a new grove is sprouting from a recent fire. And far beyond that, an ancient part of the forest remains untouched, still growing. There's no single story for the whole forest, only the story of each place. Our observable universe is one clearing. Its fate seems sealed by dark energy's pull and the slow burn of entropy. But what about regions forever beyond our horizon? The equations of inflation and quantum theory suggest other possibilities aren't just likely, they're inevitable across an infinite landscape. Some regions of the greater cosmos might still be inflating, stretching at speeds that make our expansion seem motionless. In those realms, space is being born so fast structure can never form. It's a perpetual, explosive dawn. Other regions might have recollapsed long ago. A local Big Crunch where gravity overcame expansion, pulling billions of galaxies back into a singularity. That singularity could have then rebounded, sparking a new inflationary epoch, a new universe budding off from the old. That's the concept of cyclic or bouncing cosmologies, but not for the whole, just for isolated pockets in the infinite whole. And in the vast, quiet stretches approaching heat death, quantum mechanics offers a bizarre hope. In a vacuum that's existed for near eternity, random fluctuations can give rise to new possibilities. Given enough time, and infinity provides more than enough, a random quantum fluctuation could spontaneously generate a new inflationary patch. A new Big Bang in the darkness. This isn't science fiction. It's a consequence of known physics applied to timescales that numb the mind. In a universe infinite in both space and time, these rare events are certain to happen. Not once, but an infinite number of times. So while our local sky is destined to grow dark, the greater cosmos may be a tapestry of eternal renewal, a mosaic where every possible cosmic history is being written. Some regions are dying, some are being born, some are in a stable, eternal stasis. There's no curtain call for reality as a whole. The show has no end, and it has no single stage. That transforms the narrative from a tragedy with one final act into an endless anthology. We're living through one chapter in one volume on a shelf that stretches forever into the dark. Our fate is real and poignant for us, but it's not the only story being told. The true scale of the universe suggests the deepest comfort and the deepest loneliness are both illusions. Nothing truly ends and nothing truly repeats. It just continues in forms and phases beyond our capacity to witness or even to dream. Light tells us a story, but that story has an end. There's another messenger, one that moves through reality itself. Gravitational waves. These aren't waves of light, they're ripples in spacetime. Einstein predicted them a century ago. When massive objects collide, black holes, for instance, they shake the universe. That tremor moves outward at light speed. It stretches and squeezes space as it goes. We've built observatories now that can feel it. LIGO, Virgo. They've listened to black holes merging, neutron stars colliding. It opened a new window. But the crucial point is this: gravitational waves travel at light speed. They're bound by the same horizon. The waves from a merger beyond our light horizon can't reach us any more than the light can. For mapping what's beyond our view now, they hit the same wall. Their real potential isn't in the present, it's in the deepest past. In the first sliver of a second after the Big Bang, during inflation, the universe should have been ringing. Quantum fluctuations in the infant spacetime were magnified to cosmic scales that created a background sea of primordial waves. These aren't from black holes. They're fossils from the birth of spacetime itself. They've been traveling for 13.8 billion years, permeating everything. If we could detect them, they'd carry information from before the cosmic microwave background. From when inflation began, or even from what might have come before, their pattern could encode the energy scale of inflation. It could tell us about the geometry of the universe at energies we can never reach. More speculatively, their statistical signature might hold clues about the greater landscape, the meta-universe where our bubble formed. Were there transitions between vacuum states? Do the waves show imprints of our bubble colliding with another in that early foam? These waves would be a direct signal from the whole, a faint echo of the architecture that gave rise to our local reality. Detecting this background is the next great challenge. Ground-based detectors like LIGO aren't tuned for these universe-spanning ripples. The wavelengths are too long. The hope is in space-based observatories, future missions that could measure how these ancient waves affect light from distant pulsars, or create unique patterns in the cosmic microwave background itself. It's a hunt for the faintest whisper, a whisper from the moment everything began. This changes the search for scale. We're not just looking for more distant galaxies. We're listening for the vibrations of creation. A successful detection wouldn't show us a specific galaxy beyond the horizon. It would tell us about the fundamental rules of the stage. The stage upon which all galaxies, seen and unseen, are arranged. It would be our first empirical clue about the true nature of the meta-universe, perhaps our only one. The horizon for light is absolute, but the fabric of space might still remember its origin and whisper its secrets if we learn how to listen. Gravity waves come from the past. But quantum mechanics says the present is always dividing. At the smallest scale, particles are in a haze of possibilities. Until you look, that's the measurement problem. An electron can be in two places at once. That's superposition. Measuring it forces one outcome, but the other possibility. It doesn't just go away. One answer is the many worlds interpretation. It says reality splits. Every quantum event with more than one outcome causes the universe to branch. One branch has what we see, the other branches hold every other outcome. Each in its own new universe, equally real. This isn't a metaphor, it's a proposed solution to the equations. Every instant for every quantum event, reality is forking into a vast, growing tree of alternate histories. It's a different kind of multiverse, not bubbles of space with different laws, but branches of time stemming from our own moment. So an alternate version of our universe exists right now, in a parallel branch, where you made a different choice a moment ago, or where an atom decayed at a different time. The scale is staggering. The cosmological multiverse suggests spatial infinity. The quantum multiverse suggests an infinity of timelines, constantly multiplying. The true totality isn't just more space, it's more versions of our own story, multiplying with every quantum flicker. This ties the largest and smallest scales together. What's beyond our cosmic horizon might not just be more galaxies. It might be other versions of those galaxies, living out different histories, a universe where the asteroid missed, or where life never arose. It's a dizzying expansion. Every conceivable variation of reality isn't just out there somewhere, it's branching from here now. This interpretation is controversial, but it forces a question. If every possibility is realized in some branch, then what might have been is an illusion. Everything that can happen does happen somewhere on the tree. Our experience feels singular and linear, but the math suggests we're just one thread in an endlessly branching tapestry of now. The bedrock of cosmology is this assumption that on the largest scales, the universe looks the same everywhere. In every direction. That's the cosmological principle, homogeneous and isotropic. It lets us take what we see locally and extrapolate it out, to talk about the universe as one thing with properties we can measure. But this principle is based on a sample size of one, our observable bubble. And if that bubble isn't typical, if the principle breaks down beyond what we can see, then everything we think we know about the greater cosmos could be wrong. So we look for cracks, and we've found a few. One of the most discussed is the cosmic dipole. The cosmic microwave background is almost perfectly uniform. But there's a subtle, large-scale pattern. One half of the sky is very slightly warmer than the other. The standard explanation is our own motion. The Milky Way is moving, and like running into rain, we see a Doppler shift. Warmer in the direction we're headed, cooler behind us. That's the kinematic dipole, but some studies looking at distant quasars or radio galaxies suggest the dipole might be too large. Larger than our local motion can explain. Could part of that signal be coming from the universe itself? A genuine anisotropy, a preferred direction that would violate isotropy. It would mean the universe has a grain, a fundamental lopsidedness. Then there are other curiosities, that large cold spot in the CMB, a region cooler than the models predict, and strange alignments of large-scale features, sometimes called the axis of evil. Are these just statistical flukes, the product of cosmic variance, the natural lumpiness from surveying one patch of an infinite whole? Or are they clues, hints that the cosmological principle, while an excellent approximation for our local sphere, might not hold on grander scales? If it does break down beyond our horizon, the implications are profound. Our entire cosmic story changes. Instead of a uniform tapestry, the greater cosmos could be a chaotic patchwork, a megacosmos of wildly different domains. Some regions dense with galaxies, others vast, empty deserts larger than the voids we see. The physical constants themselves might vary from place to place. The strength of gravity, the mass of an electron, our local bubble with its flat geometry and its specific laws would be just one neighborhood, one climate in a cosmic continent of infinite variety. We wouldn't be in a typical place, we'd be in a habitable zone, a rare oasis where the numbers allowed stars and planets and life to form. The rest of reality might be silent and strange. So testing the cosmological principle becomes the most critical audit. We are checking the representativeness of our only data point. Every new sky survey, every deeper map, every more precise measurement of the CMB is a test. Probing for any gradient, any preferred direction, any sign our patch is special. So far, the principle holds remarkably well within what we can see. But the true test is in the darkness, a darkness we cannot see past. The answer to whether we live in a uniform cosmos or a chaotic megacosmos may remain, like the horizon, forever just beyond our reach. Inflation is the main story we tell about the cosmic dawn, but there are other stories. There's another class of theories, the Ekpyrotic and Cyclic models. They suggest something different. Our universe didn't begin from an explosive expansion out of nothing. It began with a collision in a higher dimensional space. Think of our universe, all three dimensions of it, as a membrane, a brain, floating in a bulk dimension we can't see, and there's another brain, a parallel reality, floating nearby. In the Ekpyrotic picture, these two brains move toward each other. They collide. That collision deposits a huge amount of energy into our brain, and that's what we experience as the hot, dense state of the Big Bang. So our universe isn't an expanding bubble from a point. It's the aftermath of a cosmic crash. This idea solves some of the same problems inflation does. The horizon problem, the flatness problem, but it does it through a completely different mechanism. The scale here isn't just about more space beyond our horizon. It's about the bulk dimension itself, the higher dimensional arena where these collisions happen. Our entire observable cosmos is just the surface of one sheet, in a much grander hidden geometry, and that leads to the cyclic model. If brains can collide once, they can collide again. So in this vision, the brains oscillate. They collide, they bounce apart, and then they're drawn together again by some force across the bulk. Each collision is a big bang. It starts a new cosmic cycle of expansion and cooling. That expansion eventually gives way to a long period of acceleration, driven by dark energy, and that acceleration serves to smooth and flatten the universe. It prepares it perfectly for the next collision, Each cycle could last trillions of years. Our universe, from its hot beginning to its cold, dark end, is just one phase. In an eternal, rhythmic sequence, there is no ultimate beginning, no final end, just an endless cosmic heartbeat. This changes what beyond the horizon could mean. It might not refer to distant galaxies in this cycle. It might refer to the entirety of previous cycles, or the one that will come next. The information, the structure, the history of a universe that existed before ours is permanently beyond our reach. Erased in the fire of the last collision, but in this model, it was just as real as our own, and a future cycle will one day inherit a cosmos smoothed by our expansion. It will give rise to new galaxies, new stars, potentially new forms of life, with no memory of our story. The immensity here isn't spatial, it's temporal. An eternity of cosmic seasons, each with its own spring of creation and winter of dissolution. These models open another possibility. Each collision, each new cycle, might not produce an identical universe. The physical constants, the very laws of nature, could be slightly reshuffled each time. Our universe, with its precise tuning for complexity, might be one outcome. In a vast ensemble of cycles, most of which are sterile and silent, we find ourselves in a cycle where physics allows observers, not because of a singular fine-tuning at the beginning of time, but because in an eternal sequence, every possible combination of laws will eventually occur. So the focus shifts from what lies spatially beyond our light cone to what came temporally before our Big Bang and what will come after our universe grows cold. It frames our entire cosmic drama not as a one-act play, with a definitive start and finish, but as a single performance in a repertory theater that has always been running and always will be. Black holes are cosmic prisons. Their walls are made of gravity. The event horizon is the boundary. Once something crosses it, there's no coming back, not even light, it just vanishes. A one-way door, and that creates a parallel. We're inside a kind of horizon too, a cosmic one. It's not made by gravity, but by the expansion of space. The speed of light is finite. We can never get a signal from beyond that line. In both cases, the horizon is a veil. It separates what we can know from what's hidden forever. This similarity isn't just a metaphor. It points to a crisis in physics. The black hole information paradox. Einstein's theory says anything that falls into a black hole is gone. The information, what made a star, a planet, a book, is destroyed at the singularity. But quantum mechanics says information can never be truly destroyed. It has to be preserved even if it's scrambled. So which is right? Is the universe forgetful, or does the information get out somehow? For a long time, this was a puzzle about extreme objects in space. Then an idea came from work by physicists like Bekenstein and Hawking. They found a black hole's entropy, a measure of its hidden information, isn't proportional to its volume. It's proportional to the area of its event horizon. That was the first hint of holography. The idea that all the information about what fell into a three-dimensional black hole could be encoded on its two-dimensional surface. Like a fingerprint smeared on the sphere of no return. If that's true for a black hole, could it be true for our universe? Our cosmic horizon is also a two-dimensional sphere around us. The holographic principle asks if everything we experience, every galaxy, every thought, might be a projection from information stored on that distant boundary. In that view, asking what's beyond our horizon is the wrong question. The outside isn't more space, it's the projector. The complete description of our reality exists right here, on the limit of what we can see. Studying the physics at a black hole's event horizon gives us tools. Quantum mechanics and gravity collide there. The quantum fluctuations, the entanglement of particles across the boundary. The way information might leak back out as subtle radiation. These aren't just black hole curiosities, they're probes. probes into the relationship between information, space, and reality itself. So the microcosm of a black hole's horizon could hold the key to the macrocosm of our unobservable universe. It suggests the cosmos beyond our light might not be lost in principle. Its influence, its data, might be imprinted in the structure of our observable bubble, in the patterns of the cosmic microwave background, in the large-scale distribution of galaxies. We may never see those distant realms directly, but their shadow could be written into the code of our local reality. The event horizon of a black hole is a laboratory. A laboratory for the ultimate horizon we all live within. By deciphering how information survives a gravitational prison, we might learn how to read the story of the whole cosmos. A story written on the walls of our own celestial cell. That principle of infinite possibilities, it has a consequence. If the cosmos is endless and planets are common, then the number of worlds with intelligence has to be infinite too. Life isn't just a chance event, it's a statistical certainty. It repeats without end. The universe should be buzzing with civilizations, but when we look out, we hear silence. That's the Fermi paradox. Where is everybody? That silence is a puzzle, and one possible answer: it isn't about biology, it isn't about technology, it's about geometry. It's about the horizon. Imagine a civilization not unlike our own on a planet in a galaxy 100 billion light years beyond what we can see. They build telescopes. They listen, they might even look our way, but the light from our sun, any signal we've ever sent, it hasn't reached them, and because of dark energy, it never will. The space between us is expanding faster than light can cross it. We are to each other forever beyond the cosmic horizon. They are in their observable bubble. We are in ours, and those bubbles, they're not touching, they're flying apart, so a universe teeming with intelligence could still appear silent. Every civilization is an island, born in a sea of stars, but destined to watch as all the other islands slowly vanish over the edge. The accelerating expansion pulls the curtains closed. It makes the universe not just vast, but permanently partitioned. The scale itself is the barrier. The very thing that makes life inevitable also makes cosmic community impossible. That's a sobering resolution to the great silence. We might not be alone. We might be surrounded by a chorus of other voices, but we are all singing into a void that swallows the sound. Our search then, it becomes a poignant effort. We're listening for whispers in a storm, hoping to catch a signal from an island just close enough that its light hasn't yet been lost to the tide. The laws of physics lock us in. We won't see a galaxy past our cosmic horizon, but science isn't about accepting limits. It's about finding cracks. Direct observation is impossible. But future technology offers a different path. We may never see those territories, but we might learn to read their shadows. Our best window is still the cosmic microwave background. That ancient light is already a fossil, but we've only started to decode it. Future observatories with far more sensitivity will study its polarization. The way that light vibrates, in that subtle pattern, theorists think we might find the faintest imprints, scars from events before or during inflation. The stretching of spacetime itself could have left a distinct swirl in the polarization, a signature called primordial B modes. Detecting that would be a direct glimpse into the universe's first fraction of a second. And then, more speculatively, that polarization could hold evidence of collisions. If our universe is one bubble in a multiverse, other bubbles may have bumped into ours in that early, hyper-expanding foam. A collision like that would send a ripple through our local spacetime. It would leave a unique, circular pattern in the CMB, a cosmic bruise, evidence our reality once touched another. Finding that pattern would be monumental. It would turn the multiverse from a theoretical idea into an empirical inference, a story written in the oldest light we can see. Then there's the messenger of spacetime itself. Gravitational wave astronomy is just beginning. Current detectors listen for black hole mergers, but future observatories in space will tune to a different frequency. They'll hunt for the stochastic background, a sea of ripples from the earliest moments. In that hum could be signatures of cosmic strings, defects in spacetime that formed as the universe cooled and its forces separated. These hypothetical, dense filaments would whip through space. They'd generate gravitational waves as they vibrate and decay. Detecting them would tell us about symmetry breaking in the primordial universe. About the conditions when everything was connected. It would be another indirect clue about the architecture of the whole, so our quest is statistical. We'll never have a photograph of a supercluster beyond the horizon, but by pushing our instruments to their limits, we can gather overwhelming statistical evidence. We can measure the distribution of galaxies and voids within our observable sphere with such precision. Any deviation from expected randomness could point to an influence from a larger structure outside. It would be like studying ripples in a pond to deduce the shape of a stone thrown in long after the stone has sunk. We're detectives in a locked room. We can't leave to survey the scene, but we can analyze every speck of dust, every faint echo, every subtle distortion of light in our chamber. From that evidence, we try to reconstruct the world outside. The grander cosmos may forever be a silhouette, but with enough patience, we might one day trace its outline in the dark. We always looked up to find meaning. For thousands of years, the night sky was a story. It was a dome. Gods lived there, heroes were placed there, constellations wrote the fate of nations. That sky felt close, it had a top, it had edges. Our myths put human drama at the center. The size of everything wasn't a fact yet, it was just a canvas. For our hopes, for our fears, then in the last century that dome broke. We found out the stars aren't lanterns, they're other suns very far away. Our galaxy is just one island. And all of it, everything we can see, might be a tiny speck in something infinite. That new scale changes more than science, it changes our stories. Our deepest stories take the idea of creation. For most of history, our origin was singular. It was dramatic, it had a purpose. An infinite cosmos challenges that. If our universe is one bubble in a bigger, eternal meta-universe, then our Big Bang wasn't the beginning. It was a local event, one of maybe infinite beginnings. So there's no single moment of creation, just an endless process. The foundational myth shifts from one genesis to eternal recurrence. Our story becomes one chapter. In a library with no last book, this scale also challenges a central Earth. The Copernican idea moved us from the center of the solar system to the edge of a galaxy. The scale beyond the horizon moves us further. It suggests we aren't central to reality. We're a local phenomenon. In an infinite cosmos, every possible story is being told somewhere else. That can feel like a demotion. The comforting idea of a universe made for us just evaporates into the cosmic dark, but human creativity adapts. It doesn't retreat. Modern science fiction is the new mythology. It deals with these immense ideas directly. Multiverse stories explore the weight of infinite versions of ourselves. Generation ship tales confront the vastness between stars. That vastness feels more poignant now because we know the expansion is accelerating. These aren't just fantasies. They're thought experiments. They're how we feel the data from our telescopes. They let us feel the awe and the dread of a universe where we are impossibly rare. And also statistically inevitable. That feeling has a name, the Sublime. It's the mix of awe and terror from confronting something vastly greater, a mountain. A storm, the endless ocean, the true scale of the universe is the ultimate sublime. It brings a dizzying awe at the sheer grandeur of existence, and it can bring a deep existential dread. The realization of our smallness, our temporary nature, our isolation in the expanding dark. But this isn't just despair, it's also a source of new meaning. Our old myths gave us gods to worship, heroes to emulate. Our new scientific myth gives us a different role. We are the universe become conscious, looking back at itself. In this vast, indifferent expanse, the fact that a tiny part of it has awakened, to wonder, to ask questions, to feel this sublime mix, that is not insignificant. It's the most remarkable local event we know. We haven't abandoned myth. We just traded Olympus for the Oort cloud, Valhalla for the Virgo supercluster. The characters are now inflationary fields, quantum fluctuations, colliding brains. The stories are about cosmic dawn and heat death, but the human drive is the same. To understand where we came from, to find our place in the story, and to somehow, against all the evidence of our smallness, feel that our moment of awareness matters. The infinite scale doesn't erase our search for meaning. It just sets the stage for it on the grandest canvas imaginable. This infinite replication of our lives, it creates a quiet ethical problem. If every choice you make is also being made by an infinite number of other versions of you out there in the cosmos, does that choice lose its weight? Some philosophers think it could. If every tragedy is balanced by a version where it was avoided, and every triumph is mirrored by a version of failure, then our local story, it seems to lose its stakes. That's a potential path to a kind of cosmic nihilism, the idea that in an endless tapestry, no single thread defines the pattern, so why care about the color of your own? But there's a powerful counterargument. It focuses not on the copies, but on the immediate, singular flow of experience. Your consciousness, right here and now, is not shared with those distant copies. It's a unique, local phenomenon. The joy you feel, the pain you endure, the love you give, these are real to you. They are the substance of your reality. The fact that similar patterns of neurons might be firing in a galaxy a trillion light-years away, that doesn't lessen the vivid, present truth of your own experience. Meaning isn't a cosmic resource to be diluted across infinity. It's generated in the moment by the act of living. In this view, the infinite scale doesn't erase significance. It frames it. It tells us that significance isn't a property granted by being the only instance. It's a quality of conscious awareness itself that leads to a second, maybe heavier, ethical consideration. We have to confront the opposite possibility. What if we are not one thread in an infinite tapestry? What if, within our entire observable universe, this 93 billion light-year sphere of everything we will ever know, we are utterly alone? The silence of the Fermi paradox could mean that intelligent life is vanishingly rare, that in this entire bubble of reality, we are the only ones who have looked up and asked these questions. If that's true, then our responsibility becomes almost unbearable in its magnitude. We become the sole stewards of a cosmic memory. Every book written, every symphony composed, every act of kindness, every hard-won insight into the nature of reality, it all exists here on this pale blue dot. If our light goes out, it's not just a human tragedy. It's the erasure of a particular story from this entire volume of space-time. The universe in our local region would return to silence with no record that it ever understood itself. This idea imposes a profound duty, a duty to preserve, to endure, to ensure that the flame of awareness, however it flickered into being, is not snuffed out by our own hands. It makes the project of civilization not just a pursuit of comfort, but a sacred act of cosmic curation. So the scale of the universe presents us with two profound ethical mirrors. In one, we see our actions infinitely reflected, challenging us to find meaning in the face of repetition. In the other, we see ourselves utterly alone, challenging us to bear the weight of being unique. Both visions, they come from the same scientific models, and they force a reckoning. They ask us to decide what matters, not because the universe dictates it, but precisely because it does not. Our ethical dimension isn't written in the stars, it's written in our response to them. Whether we are a unique song or one verse in an endless chorus, the act of singing it with care, with curiosity, and with compassion, that's the choice that defines our chapter in the dark. There's another idea that redefines scale entirely, the simulation hypothesis. It says our universe might not be a physical place, it could be a digital construct. A post-human civilization with technology we can't even imagine could be running a detailed simulation, and we're inside it. Everything we see is part of that simulation. So the scale we talk about, the billions of galaxies, the vast distances that might not be distance, it might be data, it's a rendering like a cosmic video game. And we're the characters. Think about a modern video game, an open-world game. The game engine doesn't render the whole world at once. That would take too much processing power. Instead, it loads the terrain right around your character. The distant mountains, the far-off cities, they're just low-resolution placeholders, lines of code waiting to be called. Only when you move toward them does the system fill in the details. It creates the illusion of a continuous, vast world. Our cosmic horizon might work the same way. The observable universe, that sphere, 93 billion light-years across, everything we can see that could be our rendered zone. The galaxies inside are fully realized. Their light is calculated and displayed, but what's beyond that horizon? In a simulation, it might just be unrendered data, blank space in the memory. Or maybe it's a lower resolution approximation, a statistical model of what should be there. It would only get fleshed out with stars and planets if we ever tried to go there. The limits we see in physics could be processing constraints. The speed of light, that ultimate speed limit, might be the clock speed of the simulation. The maximum rate information can be processed between points. Quantum mechanics with its fuzzy probabilities, where outcomes depend on observation, that could be the code optimizing processing power. Only calculating definite states when it has to. The Planck length, the smallest meaningful unit of space, might be the pixel size of reality, the fundamental resolution. This is all speculative, of course, untestable right now, but it uses scale to ask a different question. If we're in a simulation, then the true scale of everything isn't spatial. It's computational. The grandeur of the cosmos isn't measured in kilometers. It's measured in the processing power required to simulate every particle, every force, every conscious thought inside it. Our horizon isn't a barrier of light and time. It's a buffer zone in a digital architecture. That doesn't make our reality less real. The emotions we feel, the discoveries we make, the connections we have, they're our experienced truth. But the substrate of that truth might be informational, not material. It reframes the search. We're not just astronomers mapping galaxies. We might be lines of code trying to reverse engineer the program we're running on. Trying to understand the nature of the programmers who wrote it. The silence beyond our horizon, in this view, isn't empty space. It's the quiet hum of a processor, waiting for its next instruction. The silence we're in, it's not the end. It's where the questions start. Our whole picture of the cosmos, it's built on things we don't know. And each one of those is a door to what's beyond what we can see. We have a model, but the engine of that model, we don't know how it worked. Cosmic inflation. We know it happened, but the physics of that expansion, it's still a theory. We don't know the field or the particle that drove it. Finding that would tell us about the energy of the early universe. It could tell us if our bubble was a one-time event or something common. The answer is there, in the patterns of the cosmic microwave background, waiting for an instrument sensitive enough to read it. Then there's dark energy, the force shaping how everything ends. We know it's making the expansion accelerate, but we don't know what it is. Is it a constant property of space like Einstein thought? Or is it a field that could change, get stronger, or decay over time? The future of everything we can see, and whether we can ever know what's beyond it, it depends on that answer. If dark energy's strength changes, it rewrites the forecast completely. Projects like the Dark Energy Spectroscopic Instrument, future space telescopes, they're measuring the expansion history. Looking for any shift, any clue that would crack this open, these tools, they're part of a new kind of map-making, the Vera C. Rubin Observatory with its huge mirror and camera. It's starting a 10-year survey. It won't just take a picture, it'll make a movie of the universe, tracking billions of galaxies, how they move. It'll map the cosmic web in finer detail than ever. And it'll look for anomalies, statistical ghosts, imprints from structures too large to belong in our bubble. The Nancy Grace Roman Space Telescope, too. It'll look in the infrared, trace the influence of dark energy across time. These observatories, they're forensic tools. They're examining the crime scene of our local universe for evidence left by a reality much bigger than the scene itself. On the theory side, the work is just as bold. The string theory landscape, all those possible vacuum states, it gives a framework for a multiverse of bubbles. Research is trying to bridge quantum mechanics and gravity to find a theory of quantum gravity, one that can describe the singularity inside a black hole, or the first moment of our universe. Some are even looking at time itself, asking if it's fundamental or an illusion emerging from a deeper, timeless quantum state. These aren't just abstract puzzles, they're attempts to read the source code of reality, to understand the rules that would apply not just here, but in every possible pocket of existence. Every anomaly in the cosmic microwave background, every slight deviation in where galaxies are, every new insight into quantum entanglement and spacetime. They're all clues. We're detectives piecing together a portrait of a suspect we can never see. These unanswered questions, they're not a failure, they're the compass. They show us where to look next in the dark. Each step forward, each new map or equation, it brings us closer to understanding not just the story of our own island, but the laws of the whole archipelago. We're deciphering the grammar of a language spoken across an infinite expanse, and we've only just learned the alphabet. The silence of those questions changes you. It changes you inside. Learning the universe might be infinite. It doesn't just change the map, it changes the one making the map. There's a shift that happens, a psychological one, when you really take in that scale. Astronauts know this. They call it the overview effect. You see the Earth from orbit, a fragile blue marble against the black, and all the borders, the conflicts, they just dissolve. It creates a connection, a sense of stewardship. Now take that feeling and stretch it across 13.8 billion years, across an endless expanse of galaxies. That's the cosmic overview effect. It's a scaling exercise, a staggering one. The first wave is often insignificance, a crushing sense of it. Our planet is a speck. Our sun is one of hundreds of billions in this galaxy alone. And our galaxy is one of maybe 2 trillion in the observable sphere, and that sphere itself might be a tiny bubble in an infinite meta-universe. In that context, your personal worries, national disputes, even global history, it can seem vanishingly small, like ants arguing over a single grain of sand on a beach that never ends. That can trigger something, a kind of anxiety, cosmic vertigo, but that's just the first step. If you sit with it, something else can emerge, a connection, a profound one. The same physics that spins a distant quasar, it governs the electricity in your heart. The carbon in your cells was forged in a star that died before our solar system was born. You are not a bystander, you are a temporary arrangement of ancient recycled stardust, now conscious, now looking back at itself. That isn't insignificant. It's a miraculous local event. So you have this dual awareness, our extreme smallness and our extreme rarity. That's the modern skill cosmology asks of us, holding 2 truths at once, seemingly contradictory. Yes, our individual dramas are cosmically trivial, And yes, the fact that this tiny corner has produced beings who can comprehend that triviality, that is a wonder, a breathtaking one. This perspective doesn't erase our problems. Poverty, injustice, the environmental crisis, they're still urgent, they're real on the human scale, but the cosmic view reframes them. It strips away the artificial divisions. Ideology, tribe, from 1,000,000 light-years away, there are no nations, just a species clinging to a watery rock, its conflicts rendered invisible that can inspire an ethic. A powerful one, universal stewardship. If we are, in our entire observable horizon, the only voices in the silence, then preserving this flame of awareness becomes a sacred duty. Our most sacred duty, it challenges the ego not to destroy it, to expand it, to see yourself not as the center of a story, but as a conscious participant. In the grandest story there is, the ultimate application of cosmology, it isn't just in telescopes or equations, it's in the quiet moments, looking up at a starry sky and feeling two things at once, awe at the immensity and a deep, humbling gratitude for your own fleeting chance, your precious chance to be part of it. Teaching the size of the universe is a problem of imagination. Our minds evolved to watch for lions on the plains, not to understand distances where light travels for billions of years. So you have to build a ladder. You start with what's known, a globe in a classroom, then you pull back, you see the solar system. If the sun is a basketball in New York, Earth is a marble about 80 feet away. Pluto is a speck of sand more than half a mile from that basketball, and that's just our own system. The next closest star, Proxima Centauri, on that same scale, would be another basketball placed in Los Angeles. The emptiness starts to become real. Visuals are necessary. A planetarium show is one of the strongest tools. It doesn't just tell you the galaxy is large. It takes you begin above your own city, then you pull away, the continent becomes a shape. Earth turns into a blue marble, then a faint dot swallowed by the sun's light. The solar system is a swirl of paths, then just a spot as nearby stars fly past, shaping the arms of the Milky Way, and you continue until our galaxy is one of many, many specks in a giant web-like structure. That visual trip does what language can't. It goes around the thinking mind and gives you a sensation, a sense of scale. Comparisons are another rung on that ladder. The common one is the grain of sand. Take every star we can see, all of them, shrink them down to one grain of sand. That grain is our entire observable universe. Now imagine a huge, empty beach, stretching out in all directions farther than sight. That beach is the possibly infinite universe beyond what we can see. Our grain of sand rests on it, alone. That comparison is sobering, but it's also imperfect. It still uses a thing, a beach, which has an edge in our imagination. Real infinity has no edge. That's where understanding stops. Good teachers admit that stop. They say, it's fine if this doesn't completely fit. Our brains weren't made for it. The aim isn't to see it perfectly. It's to know that the model is pointing at something bigger than we can picture. Step-by-step scaling works. Take a normal sheet of paper. Imagine its thickness is the distance from Earth to the Sun, 93 million miles, one sheet. To reach the nearest star, you'd need a stack of paper over 4 feet tall. To cross the Milky Way, a stack over 300 miles high. To get to the Andromeda Galaxy, a stack that goes past the Moon. That step-by-step method makes the huge leap feel solid. The last step matters most, linking the cosmic scale back to us. It's not about feeling tiny, it's about feeling linked. The same physics, the same ancient elements are right here. In this air, in the people around us, we are the universe looking at a small, bright piece of itself. The awe you feel when you finally see the scale, that's not the finish. It's the start of a different kind of wonder, one that can stay with you. That feeling of awe, that sense of a deep mystery, it's something people have felt across history. It's where science and the search for meaning have often met. For so many questions about the scale of the universe, its origin, they're not just scientific. They're spiritual. The Big Bang, this moment of creation from an incredibly hot, dense state, it resonates with certain creation stories, and then there's the fine-tuning. The way the fundamental constants seem perfectly set to allow for stars and planets and life. Some see that as evidence of design, a signature. For others, the answer is different. It's the idea of a multiverse, an eternal landscape. Our universe isn't a singular, fine-tuned artifact. It's one bubble among countless others. We just happen to be in one where the numbers accidentally work. That removes the need for a singular creative act. It makes our reality a statistical inevitability. But this tension, it doesn't have to be a battle. The dialogue between science and faith can be a search for different kinds of truth. They address different layers. Science, with its observation and math, describes the how of the cosmos. It maps the expansion from a singularity. It details the life of stars. It theorizes about dimensions we can't see. It gives us the mechanics of the symphony. And many faith traditions, they grapple with the why. Purpose, value, ethics, the source of consciousness itself, realms science isn't built to judge. They offer a framework for meaning within the vast narrative science reveals. That immense scale itself beyond our horizon, it can be a source of spiritual awe. Confronting a cosmos that might be infinite and eternal, it evokes that same feeling of the sublime, the mix of terror and reverence before something infinitely greater. This isn't a retreat from understanding, it's an expansion. The more we learn about the universe's grand architecture, the more we're reminded. A profound mystery remains at the heart of existence. That shared sense of mystery, from looking honestly at the stars and the dark between them, it can be common ground. It reminds us that this quest to understand our place, it's a deeply human one. These huge questions can seem far away from everyday life, but that link is actually there, and it's practical. Trying to map the cosmos has always pushed our technology forward in ways we didn't see coming. Take GPS. The satellites up there have to account for relativity, both special and general. Their clocks tick at a different rate than clocks down here because of their speed and the weaker gravity. If engineers didn't use Einstein's equations, the same ones that describe the universe's curvature, the location data would drift by miles each day. So navigating a city street is tied directly to understanding spacetime. And that pattern keeps repeating. The drive to see further into space demanded better optics, better sensors. The charge-coupled device, the CCD, was perfected by astronomers to catch faint starlight. That same technology became the heart of digital cameras, smartphone cameras. It changed how we document our own world. Medical imaging, CT scans, MRI machines, they used techniques and math that came from fields like particle physics and radio astronomy. Even the Internet's infrastructure was shaped by the need at CERN for physicists to share huge datasets across continents. The tools we use to connect, to heal, to see, they're often byproducts of looking upward. Pushing the observational frontier means constant innovation. Building the next big telescope isn't just about a bigger mirror. It needs new materials that won't warp in the cold of space. It needs advanced computing to process petabytes of image data, algorithms to filter cosmic signal from noise. These challenges force invention, and those inventions eventually filter into other fields: manufacturing, data security. Investing in fundamental cosmic science is investing in a future toolkit we can't yet picture. But beyond technology, this perspective gives something else. A framework for thinking. Cosmology teaches thinking in deep time on planetary scales, that climates change, that celestial impacts reshape worlds, that the conditions for life are delicate. This long-term view isn't a luxury. It's essential for the existential challenges we face right here. Confronting global climate change requires seeing Earth as a single, fragile system, a perspective any cosmologist would recognize. Planning planetary defense against asteroids uses the same orbital mechanics we use to track distant comets. The cosmic overview effect, that feeling of connection and stewardship, becomes a psychological resource. It fosters a cooperative, forward-thinking mindset, the kind we need to safeguard our future. Understanding our tiny place in the vastness isn't about feeling small. It's about clarifying what matters. It sharpens the vision for humanity's long-term trajectory. Are we a species that looks outward, learns, innovates, cares for its home? Or do we turn inward, consumed by short-term conflicts on our speck of dust? The study of the cosmos argues for the first one. It makes the case that curiosity is our greatest survival trait. By reaching for the stars, we end up learning how to better tend the garden we stand in. So the greatest practical implication of cosmology might be the wisdom it plants in us. The realization that our most abstract questions about the universe are, in the end, deeply practical questions about ourselves. That clear night sky is your own gateway. The light from those stars has traveled for years, centuries, to meet your eyes. You're not just looking at points of light, you're receiving ancient messages. In that quiet moment, you become part of the cosmic conversation. It's not about having the right equipment, it's about a shift in perception, a shift that's available to anyone, anywhere. You stand on a planet, orbiting a star, drifting through a galaxy that's one of trillions, and you are made from the same elements forged in those distant furnaces. That simple fact is an anchor. It roots the vast, abstract scale in your own physical being. You are not separate from the cosmos you observe. You are its conscious expression. Wondering about the horizon, the infinite dark, is not a passive exercise. It's an active engagement with reality. It's the human mind reaching out, trying to touch the edges of its understanding. Every great discovery in history began with that same quiet sense of wonder. Someone looked at the ordinary world, a falling apple, a swaying lamp, the path of Mars, and asked a question that had no ready answer. That spark of curiosity is our shared inheritance. It built our civilizations, our tools, our art. And it's what now compels us to build telescopes that peer back in time, to craft equations that describe realities we may never see. When you feel that awe under the stars, you are participating in the same fundamental drive. You are keeping the question alive. The scale can feel overwhelming, but wonder makes it intimate. It transforms the universe from a cold, distant fact into a living mystery that includes you. So the next time you step outside and glance upward, pause. Let the distance sink in, let the silence speak. That act of looking, of wondering, is a celebration of the curious creature we are on this tiny world, daring to ask what lies in the great dark beyond. Our search for answers may never be complete. The horizon may forever recede, but the wonder itself, that is the destination, and it is always within reach. We traveled a long way, from the stars we know, out past the edge of everything we can see, and that trip shows us one thing. Our home, the cosmos, is probably much bigger and stranger than the little bubble of light we call the observable universe. It might be truly infinite or just so huge we can't grasp it. But either way, what's beyond our horizon changes things. It changes how we see what's real. It challenges our ideas about purpose, about being unique. It pushes against that need to feel like we're at the center of everything. The walls of our prison, the ones made of light, aren't the walls of the universe. They're just the limit of what we can see right now, and they keep moving back into a dark we might never see into. We may never get a picture of what's out there. A direct photo, but that's not the point. The point is the looking, the questioning, trying to build an idea from the faintest signals in the static. That's what stretches the mind. It pushes imagination to the edge and then asks for more. The universe doesn't have to make sense to us. it doesn't have to fit our stories. Its scale, the possible infinities, the strange ideas about it being holographic or cyclical, they tell us reality didn't sign that contract. Our job isn't to force it into a box we understand. It's to have the courage to follow the clues, no matter how weird it gets. So take that feeling with you, that sense of wonder, use it to look at your own world. The big conflicts, the immediate worries, they're all happening on a speck of dust, floating in an ocean of scale and mystery. This view doesn't make our experience smaller. It puts it inside the biggest story there is. It makes our short moment of awareness, our ability to love and wonder and create, feel more precious, not less. For a little while, we are the universe looking at itself and asking what else is there.